I'll just get started. Okay, so thanks, Amir, and thanks a lot for giving me this opportunity. So I'll be talking about building scalable piezoelectric platforms for optomechanics. And the piezoelectric part is key here because I'm interested in cavity optomechanical systems in which the mechanical board is driven by an external applied RF signal. So a better way to think about these devices is in terms of resonant Acousto-optics rather than in the traditional cavity optomechanics framework. So what do I mean by scaling here? So I'm actually talking about two different but slightly related ideas. The first one is scaling the system complexity, and this is an idea that's familiar to us from silicon photonics and silicon microelectronics. And this is asking the question, how can we go from the n=1 device regime to the n=1000 systems regime? So if you want to build, say, 1000 nominally identical devices on the surface of a chip, how can you do that? And more importantly, what sort of interesting applications are enabled once you're able to achieve that kind of scale and complexity? And I'll have something to say on that front. But I'm also interested in the idea of scaling the operating frequency of these Acousto-optic devices. So traditionally, Acousto-optics works well in the sub-1 gigahertz regime. And I'm interested in asking what sort of devices and geometries enable you to scale this operating frequency to the, say, 10 gigahertz frequency range. And this means moving beyond the paradigm of working with localized Acousto-optic interactions and instead moving towards traveling wave Acousto-optic interactions. And I said earlier that these two ideas are related, and it comes about because once you move towards traveling wave geometries, then you automatically move towards a circuits-like platform. And we'll see more of that later. So how does one achieve scale traditionally in any platform? The general method has been through some kind of Foundry-like architecture. And so you can do one of two things, and I'll tell you about our progress on both fronts. The first is that you can take an existing Foundry process, which has all the key ingredients, and figure out a way to modify it so that you can make it do what it wants. And so that's the first half of the talk. But one thing that we learn with Foundry processes is that they are limited in the kinds of materials that you can access. And ultimately, Acousto-optics at high frequencies, and especially if you care about high efficiency, becomes a materials problem. And so you can ask instead the opposite question. Instead of sticking with traditional Foundry platforms, can I not apply ideas from semiconductor manufacturing to the best available material? And that will be the second half of this talk. So before we spend more time talking about the devices, I just wanted to spend some time talking about why or when Acousto-optics makes sense. So because if all you want to do is build a modulator, there are many available options. In fact, both electro-optic modulators based on thin-film lithium niobate and silicon microring modulators have made enormous progress in the past couple of years, and both of these platforms can enable greater than 50 gigahertz bandwidth. So if modulator bandwidth is what you're looking for, Acousto-optics really can't compete. On the other hand, if modulation bandwidth is not the key criterion, but efficiency is, then Acousto-optics can give you some advantages. And the way to understand this is to look at that any modulator can be characterized by a generalized overlap integral and some coupling constant G, which can be written as an overlap over the modulator volume of your optical pump field with your perturbing field. So the psi omega RF is an electric field in the case of an electro-optic device, and it's the acoustic strain or displacement field for an Acousto-optic device. And so if you look at this integral, there are two ways that you can maximize this. So one is that you can enhance the magnitude of this psi omega RF, and this you can do by resonating the system, or you can increase the overlap of all the fields involved here, and thus also maximize G. And in some sense, an Acousto-optic device does both. So with acoustic devices, you can achieve much higher quality factors at high frequencies. So for example, it's relatively straightforward to get quality factors exceeding 1000 at frequencies greater than 2.5 gigahertz. On the other hand, it's very difficult for RF cavities to even achieve 100 at those frequencies. The second thing that Acousto-optic devices do is that they can help you achieve much larger spatial mode overlaps. And this happens because acoustic waves and optical waves at very different frequencies can have the same wavelength. So since the speed of sound in most materials is much smaller than the speed of light, roughly by about 5 orders of magnitude, a 2.4 gigahertz acoustic wave and a 194 terahertz optical signal can have roughly the same wavelength. And so the whole idea is that whenever you really care about efficiency, Acousto-optics is one of the best ways to go. And the real poster child for these kinds of applications is when you're looking for surface normal modulators. So anytime you want to build a surface normal device, you really care about interaction efficiency. And that's because you don't have the interaction lengths that you have available in other guided wave platforms. And so for surface normal devices, resonant Acousto-optics does provide a great advantage. And surface normal devices are used in a wide variety of platforms, and I've listed some of them here. So for example, you can imagine replacing the liquid crystals used in spatial light modulators with Acousto-optic equivalents. And this allows you to increase the response time of these pixels from about 1 milliseconds to about tens of nanoseconds. A more interesting near-term application, and something that we are currently working on, is the use of these devices to scale up ion trap-based quantum information processing systems. And so this is an image of an ion trap system from IonQ. And the main idea here is that as you have, every ion trap system basically has this multi-channel Acousto-optic device that's used to generate the individual addressing beam needed to address these trapped ion systems. So as these trapped ion systems grow in scale and complexity, the Acousto-optic platform also has to keep up and sort of provide the same trends. And it's very obvious that current methods of building these platforms do not really scale beyond the n equals 50 channel limit. And that this comes about mainly because of power limitations and the way these systems are designed. So what's the main challenge with building high frequency Acousto-optics or efficient Acousto-optics at high frequency? One can get a good idea just by looking at a commercial Acousto-optic device that you can buy from someone like Buch and Hausco. And if you look at a commercial Acousto-optic modulator, it's essentially a bulk device that is hand assembled and packaged. And it's made of non-standard materials like quartz and tellurium dioxide. And this bulk form factor essentially limits the operating frequency of these devices to below a gigahertz for efficient interactions. And so one way to imagine taking these devices and moving them to high frequency is just reducing the size so that you can engineer high frequency operations. It has been well known for some time that suspended MEMS devices can achieve this kind of scale and complexity. So here's an image of a digital light projector chip from Texas Instruments, and this is built at 4K resolution. And so the natural question becomes, can we combine the performance of an Acousto-optic device, but employ it in a MEMS-like Foundry platform so that you can get the best of both worlds? And this is what we set out to do. So we employ this Piezo-MEMS platform from MEMSCAP. This is a standard MEMS Foundry process, except that it has an additional aluminum nitride piezoelectric layer on top. And this piezoelectric layer is critical for exciting these high frequency resonances. So if you look at the layer stack, it consists of a 10 micron thick silicon layer, a 500 nanometer thick aluminum nitride layer, and a top aluminum contact. So our main reason for working with this kind of foundry process was that we wanted to engineer Acousto-optic resonances in which the frequency of both the acoustic and the optical frequency are defined by the thickness of these layers. And this is important because if you want to build anything at scale, then especially if you want to build 1,000 of these resonant devices on a chip, you need to have some method of dealing with device-to-device variability. And the best way to avoid device-to-device frequency variation is to pick a resonant frequency that is dependent on the device thickness, because you can control the thickness to much greater precision than you can control any in-plane dimension. So for example, a state-of-the-art 12-inch CMOS wafer can control the silicon layer thickness to less than a nanometer. And so, and this is an image of a device that's fabricated in this platform. Like with any other suspended MEMS platform, you basically, the silicon layer here is suspended, and this allows us to optically access the chip from the backside. So if you apply an RF signal across the aluminum nitride layer using the aluminum contact as the top electrode and the p-doped silicon as the bottom electrode, the aluminum nitride, being strongly piezoelectric, responds to the RF excitation by expanding and contracting, and the whole suspended structure starts vibrating. And if you sweep the RF frequency and measure the RF reflection spectrum, you essentially get a series of resonances that can be seen here. One of the nice advantages of working with this kind of vertical geometry is that it allows you to basically work with the D33 coefficient of aluminum nitride, which is its largest coefficient. And this is critical if you want to engineer very high efficiency RF to acoustic signal transduction. Another advantage of these devices is that the transducer design really doesn't change much as you go to high frequencies. And this means that you can get, with the same kind of transducer, you can get reasonably efficient RF to acoustic transduction across a broad frequency band. So for example, I'm showing the RF response up to about 5 gigahertz, but in the lab, we have been able to measure S11 dips all the way up to 12 gigahertz. And this is in contrast to the other kind of transducers like surface acoustic wave devices, where the transducer performance really drops as you move in the 10 gigahertz frequency range. If we look a bit more carefully at what the resonances look like, these are essentially longitudinal resonances of the cavity. And one way to think of them is these are successive acoustic Fabry-Perot standing wave resonances that are set up. And a closely related version of, so these resonances are referred to as the high overtone bulk acoustic wave modes. And a close cousin of these are the film bulk acoustic mode, or the F-bar resonances, that are dominant in RF filtering in all modern smartphones. And the reason they are dominant is because they have the same property that you can get very, very high quality factors at these high frequencies. In our case, the acoustic quality factor is somewhere between 500 to 800, depending on the particular mode of interest. And we believe our quality factor is primarily limited by the roughness of the top aluminum contact. One nice thing that we do have with the aluminum is that it does provide us with some kind of energy trapping. So you can see in these figures that the acoustic energy is primarily confined in the center of the cavity, and that primarily comes about because the aluminum mass loads the center, and you get this energy trapping effect. So again, given that we have two parallel surfaces, you can also run this device as an optical fabric mirror cavity, with the aluminum top aluminum contact serving as the top mirror. And by metallizing a thin layer of gold from the backside, you can create a bottom contact with reasonably high reflectivity. And so once this stack is set into vibration by exciting the piezoelectric resonance, the optical cavity length starts to change because this cavity starts vibrating. And if you reflect light off the backside of the chip, you essentially get modulation. And so we run this device in reflection mode from the bottom side, and this effectively runs as a reflection Acousto-optic modulator. And you can measure this modulation spectrum. So if you calculate the modulation amplitude and plot it as a function of frequency and plot it on the same scale as your RF reflection spectrum, you can see that you can only get significant modulation in this device when you hit one of these acoustic resonances. And if you look more carefully at one of these responses, so for example, the 1 gigahertz mode, you see that the S11 response shows some sort of fine structure. So there are multiple modes that are excited. And the origin of these multiple modes is because the contacts in our device are extremely symmetric. So there's a lot of spurious mode coupling that occurs inside these devices. Now, this is a problem that's been well known and well studied in F-bar devices. And the way to get rid of this is to design polygonal electrodes. In our case, as we move towards high frequencies, so close to the 2 gigahertz mode, we see that the S11 response becomes very close to a Lorentzian. And we believe that the spurious mode coupling is reduced at high frequencies, mostly because the acoustic mode is much better confined in the center of the electrode. One interesting thing to note here is that our Acousto-optic interaction is primarily dominated by the moving boundary contribution. That is, as this acoustic mode vibrates, it changes the length of the cavity, and that's the main effect that is giving us the modulation. To quantify the key parameter that you want to extract in these devices is basically how well is this cavity functioning as a modulator, and so you want to extract the modulation efficiency. To quantify the modulation efficiency, you can look at the interaction between the optical mode and the mechanical mode in the cavity with the standard optomechanical formulation. And if you treat this device as a phase modulator, you can see that the optical cavity frequency gets modulated at the mechanical frequency rate. And the parameter of interest is beta, which is the modulation index of the cavity. The modulation index can be defined as the shift in the optical cavity frequency to the applied mechanical frequency. And the shift in the optical cavity frequency is directly proportional to the cavity displacement that is induced by the applied mechanical segment. Now you can extract this modulation index beta by essentially tuning the laser, by tuning your laser across the cavity resonance and by recording the modulation amplitude at each point during the sweep. And if you do that, you basically get this characteristic double peaked response. The double peaked response happens because the modulation amplitude is peaked when the laser is tuned to the point of maximum slope, and you get a minima when you're right in the center. This is true for a phase modulator. And if you do that and by fitting this response, you can now extract what the modulation index beta is. And if you do that for all of these different modes and plot them on the scale, there is some device-to-device variation that we don't fully understand, but the beta as a function of frequency shows some general trends that we can extract. One is that the modulation index beta falls off with frequency, and the dependence is roughly 1 over f. The 1 over f dependence primarily comes from the fact that the modulation amplitude, so for a fixed RF power, the amount of cavity displacement that you can induce goes down as a function of frequency. That dependence is also roughly 1 over f. Even given that, we are able to achieve quite significant modulation index in these quite simple architectures. So for example, for a 1 gigahertz mode, we are able to see modulation index of about pi over 2. And for the 2 gigahertz mode, it's about pi over 8. If you want really strong modulation, the key is to move towards a low frequency mode. So you can see these gigantic peaks here. And for a 350 megahertz mode, which is the fundamental mode of this cavity, you can get modulation index as large as about 4 pi. But more important than the phase modulation is actually how good is this device as an amplitude modulator. So how well can you transfer power from a pump to the sideband? And so you want to directly measure the sideband power. And we can do that by sticking an RF amplifier in front of a acoustic signal. And by measuring the output transmitted power in an optical spectrum analyzer, you can directly measure the presence or absence of the sideband. And so you can see that even though we have very good phase modulation, the amplitude modulation in the structure is not so great. And one way to understand that is because this device is not a traditional Acousto-optic modulator, but a resonant version, the amplitude of the sideband roughly scales as the ratio between the modulation frequency omega m and the cavity line with kappa. So because our cavity optical cues are reasonably low, they're somewhere between 350 to 400, the ratio between omega m and kappa is about 1:100. And that is the main limitation in the efficiency of these devices. And so one of our main lines of research currently is to figure out how you can improve the quality factor of these devices while sticking within the constraints of the Foundry design process. And that's very tricky because the line widths that are available in the MEMS Foundry process are not anywhere close to what you can get with silicon photonics. But an alternative way of achieving high efficiency in these systems is to recognize that we can also work with a different modulation mechanism. So for example, I mentioned that the modulation mechanism that is dominant in our systems is actually the moving boundary contribution. And one way to see this is that every adjacent longitudinal resonance has either even or odd symmetry. And if you look at the change in the length of the cavity, the even modes give you a significant change in the total cavity length, whereas the odd modes do not show that. And so if you look at the response of the modulation as a function of what mode it is, you can see that the even modes give you strong Acousto-optic response, whereas the odd modes do not. On the other hand, we are not exploiting the Acousto-optic or the elasto-optic properties of silicon at all in these structures. So traditional Acousto-optic modulators work predominantly using the Acousto-optic effect, whereas these devices are working with the moving boundary contribution. And so one can see, okay, when can Acousto-optic effects become dominant inside the system? And so to do that, you can approximate the Acousto-optic interaction by this simple one-dimensional integral and plot the relative contribution of the moving boundary and the Acousto-optic effect inside this device. And you see that essentially for every mode inside this cavity, the moving boundary contribution is dominant until you reach about 37 gigahertz, where the Acousto-optic contribution becomes phase matched. And this happens because once you reach this 37 gigahertz point, you basically are doing Brillouin scattering inside silicon. And so in this case, you basically match the condition for Brillouin scattering, and you can get a very, very strong Acousto-optic interaction inside the structure. And so unfortunately for silicon, both the high refractive index and the large speed of sound means that the Brillouin frequency is set at around 37 gigahertz. On the other hand, if you change the material platform or basically work with a slower acoustic wave, like going from longitudinal modes to shear modes, you can bring this Brillouin frequency down from over 37 gigahertz to about somewhere between the 10 to 15 gigahertz range. And that's also something that we are currently looking at. Now, so while we've seen that we can do a few interesting things inside this process, there are some fundamental limitations that a Foundry process imposes. One of the key challenges is that you are limited in the set of materials that you can access. And ultimately, Foundry Acousto-optics at high frequencies and and especially if you care about high efficiency, ultimately becomes a materials problem. And so we wanted to ask the opposite question, that instead of working with silicon-based platforms, why not apply ideas from silicon photonics to the best available materials and see if you can improve the performance of these devices that way? And the thinking behind this meant that essentially a Foundry process at its heart is basically a set of design rules that is materials agnostic. And so you should be able to apply it to pretty much any material platform of interest. And as long as you stick within the design rules, you should be able to get the scale that you want. That was the main hope. So what is the ideal platform for Acousto-optics? So one of the key things is that if you want to build a Foundry platform from scratch, it's a very intensive and expensive endeavor. So it's good to have more than one problem to aim for. And so if you make a list of desirable optical or acoustic properties that you want in any material, 3.5s are almost ideal for this purpose. So for example, for the piezoelectric, for the Acousto-optics, they have high piezoelectric coefficients and large Acousto-optic interactions. On the other hand, a different way to interpret this same graph is to say that, okay, silicon does not have many desirable optical properties, but it tends to dominate photonics primarily because of the presence of this foundry infrastructure. And so you can say that the foundry infrastructure basically compensates for for basically lack of good optical qualities. And the question becomes, if we now take this foundry infrastructure and this way of building circuits and apply them to 3.5s, we should in principle get the best of both worlds. Now, this is not a hypothetical question because there are actually many problems, a few of which I have listed here, which ultimately boil down to being able to find the right material to engineer the efficiency. So just one out of this, if you think about what limits the scaling up of linear optic implementations of quantum information, I believe it's ultimately limited by the employment of feed-forward routines. And feed-forward, if you put it down as a device problem, ultimately comes down to being able to build extremely low-loss, high-speed cryogenic optical modulators that can work with PICs less than 100 millivolts. And this essentially is a materials problem, in my view. Even from an Acousto-optics, Acousto-optics is even more sensitive to the choice of materials. So as we saw, the current modulators that you can buy from Gaussian Housego employ exotic materials like tellurium dioxide. And this is with very good reason. And there are many ways of understanding this, but one way that we looked at it in some detail in this paper is if you look at the problem of microwave to optical signal transduction, you will see that essentially this problem comes down to being able to match your electromechanical and optomechanical cooperativity. And it turns out that in pretty much every scenario, you're limited by the achievable optomechanical coupling strength. And so one way to think about this problem is that you pick the material that gives you the strongest optomechanical interactions and then figure the rest of the things later. And if you make a list of the available materials that show the strongest optomechanical interactions, gallium arsenide stands out because it has both strong elasto-optic coupling coefficients and very slow speed of sound. So the ratios basically work in your favor. But it's not just a matter of getting stronger interactions. You can engineer qualitatively different interactions in these systems. So for example, backwards Brillouin scattering, which is very difficult to achieve in silicon because of the small magnitude of the P12 coefficient, becomes large and efficient inside gallium arsenide. And why is this interesting? It's interesting because these longitudinal modes that are involved in backwards Brillouin scattering actually are expected to have some of the highest quality factors at these frequencies. But more importantly, if you go towards 3.5 platforms, you can do things that are completely impossible in silicon. For example, you can use acoustic waves to interface to other quantum dot structures and other quantum confined structures. So before I go on to the details, I just want to clarify something that some of you may already be wondering. Don't 3.5 photonic integrated circuits already exist? And the answer is yes, they do, but they don't have anywhere near the scale and complexity that you get from silicon photonics. And the main reason is because they are built very differently. So silicon photonics circuits are built with an index contrast, refractive index contrast of about 2, whereas 3.5 photonic integrated circuits are built with an index contrast of about 0.3. This means that essentially the mode sizes are very large and your bend radii are correspondingly large in the hundreds of microns. And you have very low effective nonlinearities. And if you think from a modulator perspective, the Vπ of the modulator is very large. Another equivalent way to put it is that your component density that you can get in 3.5 photonic integrated circuits, so just the number of components per square millimeter of the chip, is much lower than silicon photonics. On the other hand, 3.5 materials have refractive indices that are very, very close to silicon. So if you build 3.5 circuits the same way, in principle, you can increase the component density by about 100x, or put it equivalently, if you want to implement some functionality, then you can reduce the size of the chip that implements some function by the same 2 orders of magnitude. And this is, and so the natural way that you can increase index contrast inside these structures is by suspending it. So if you release the sort of release the AlGas layer, you should be able to build suspended waveguide structures this way. And this is not a new idea. It's been around it's been employed by many people, including us in the past. The key question that we wanted to ask was that, can you build large photonic integrated circuits this way? So what limits the scale and complexity of what you can achieve this way? And more importantly, can you achieve a performance inside these devices which gets close to silicon? And that's what we set out to do. So we wanted to replicate a passive silicon photonics process, but implement it in a 3.5 platform. And here we got lucky because gallium arsenide has a refractive index that is very, very close to silicon at 1550, which means that Foundry designs for silicon photonics that have been optimized over almost 2 decades can be directly applied to gallium arsenide, and you can do a direct materials comparison. So essentially, since the geometry of the devices is identical, any difference in performance can be attributed to materials processing. And so that's what we do here. We essentially implement a passive silicon photonics process with 3 steps: a grating edge, a rib waveguide edge, and a full edge where we reach the AlGaAs layer. And once we reach the aluminum gallium arsenide layer, we dip the chip in hydrofluoric acid to suspend the whole structure. And once the structure is suspended, we cap the whole chip and encapsulate it in about 2 microns of silicon dioxide. And here, this is where the sort of high refractive index of gallium arsenide really helps us out, because the mode is so tightly confined to the center of the rib that you can tether the structure quite liberally without worrying about optical loss. Now, one of the traditional problems that suspended structures have faced in the past is that people have always worried about whether these structures can scale, and more importantly, do they have the rigidity to support multiple layers of post-processing. It turns out that if you design the size of these holes right, once the structure is encapsulated in oxide, the oxide ends up essentially locking the structure in place. So you can see here by this rectangle that the oxide essentially makes the structure, once the oxide encapsulates the structure, it ends up being as rigid as the starting substrate that we started with. And 2 interesting ways that we tested this was that we are able to land fiber arrays on these structures, and we are able to characterize them without any issues. And more importantly, we can stick the chip in an ultrasonic bath, and there is no visible structural damage. Now, rigidity is not only key for just for sort of post-processing, it's also critical if you want to build any kind of active devices in this platform. So for example, if you want to build electro-optic or Acousto-optic modulators, you need to add a lot of metallization on these suspended structures. And the thickness of the metal actually, or the weight of the metal actually makes these structures sag. So unless you have some kind of rigidity, it's very hard to do post-processing. So having seen that, we wanted to now demonstrate a set of passive components inside this 3.5 Foundry platform and see how their performance compared to what you can achieve with silicon. So to start with, the critical element is a grating coupler. The grating couplers are standard in silicon photonics, but they are rarely used in 3.5s. The 3.5 photonic integrated circuits mostly rely on edge coupling. Now, edge coupling is fine, except the problem is that you really can't test the chip without sort of cleaving. So you need to cleave the chip before doing any kind of testing. And so grating couplers allow you to get around this problem because you can access the chip in situ while it's being processed. And if you build grating couplers inside this platform using standard silicon designs, you can get an insertion loss that is very, very close to silicon-like numbers. So we get about 3.5 dB per coupler, which is very close to the 3 dB per coupler that silicon sees. More importantly, we want to show that you can build arbitrarily complex circuits. So you can just take silicon designs that have been optimized, for example, a 2x2 MMI, and replicate it. And you can see here that we can now get 50-50 split ratios and almost no change in the, no excess insertion loss. And this sort of verifies the importance of building Foundry platforms, because once you have a set of building blocks that are well characterized, you can build arbitrarily complex circuits by just cascading these structures. And that's what we hope to show here. One final thing that some of you may be interested in is what kind of loss numbers are we able to achieve inside these new materials. It turns out, so we built microring resonators to characterize the loss inside this platform. And our current best results basically give us loaded quality factors of about 30,000. And if you extract the equivalent waveguide loss from this quality factor, we get about 10 dB per centimeter. Although we believe our rings are slightly overcoupled here. And while 10 dB per centimeter might sound quite large inside these, compared to what we can achieve routinely with silicon, these are the very first results. And we believe by improving our fabrication process and more importantly, by passivating these surfaces better, we should be able to achieve losses close to silicon, at least in the 2 to 3 dB per centimeter range in the near term. With that, I'm almost at the end of time. So I just want to end by talking about where we are going in the near term. So on the Foundry Acousto-optics front, our main goal is to see if we can run these devices efficiently at cryogenic temperatures. So basically, can we see 10 gigahertz Acousto-optic modulation with these devices at low temperature? And the main reason of working at low temperature is that it allows us to basically to improve our mechanical quality factor. The other key direction in which we are pursuing is to scale the device architecture to allow two-dimensional arrays to move towards a spatial light modulator-like architecture. And on the Foundry side, I was hoping to show some results on active devices, but you're not yet there. So we are trying to build Acousto-optic modulators, but a more interesting experiment that we have in place is to do electromechanical guided wave stimulated Brillouin scattering. And I hope to have results on that next time. So I want to end by thanking the people who helped out with everything here and the funding agencies for supporting this work. Thank you.
Okay, thank you, Krishna. So we're a little bit behind schedule, so I'll just go directly to the next talk. And please, if you have questions for Krishna, put them in the Q&A window, and he can answer them. So the next speaker is Ines Gorbel from Talos Research, and this will be a